and welcome to the titration curve podcast of a weak acid with titrating in a strong base. Now, a lot of times you're going to be asked to interpret a pH curve, so you're going to be given a titration curve, and then you're going to have to find certain values on it. But the best way to be able to interpret a titration curve is to know how to make one. Also, in a way, this is like a theoretical curve, whereas if you actually titrate it yourself or you're given one for an experiment, that would be an experimental titration curve, and you can compare the two values to see how well you did in the experiment. Alright, so we're going to walk through an example problem. So our example problem is going to be 60 mils of propanoic, of 0.1 molar propanoic acid. So that would be the component when you actually do the titration that would go into your Erlenmeyer flask, okay? I am going to write the propanoic acid as HA because it has a big long chemical formula. All right, so what we are going to add in to the propanoic acid is going to be the KOH, which really we don't care about the K, we just care about the OH, and that's what's going to be in the burette. And that is 0.2 molar. And the reason why you're not given the volume for that is because you're actually going to find the volume, the pH, many volumes. So when you do a titration with a strong acid and base, you really only care about getting to the equivalent point and plugging it into MAVA equals MBVB, because moles of acid will equal moles of a base. And that's the whole purpose of most titrations. With a weak acid or a weak base, they can also be conjugate acids or conjugate bases. You can actually find out a lot more from the titration curve, so it's important to look at many locations. So, coming back here, this is going to be our HA. And I want to take a look at this word, standardized KOH. Remember that a lot of the things that we titrate with, the solutions, are not going to be the exact molarities that, so we're saying this is 0.2. They're not going to be exactly what we measure out. We know the potassium hydroxide is hygroscopic, which means that it picks up water in the solid form. So when you go to weigh out the pellets of KOH and you add it to make your solution, if you weigh out 30 grams or 40 grams or 50 grams, it won't quite be that mass because some of it will be water weight. And so it's really important to pre-standardize it. And you can standardize it with a standardizing acidic salt. And you can look that information up, but that's what we mean by standardized solution. So now we know that this actually is 0.2, and probably we would know several decimal points after, so we'll put 0, so that we can trust the value. Because if you can't trust the molarity of your base as you titrate it in, you really, all of your calculations are going to be off. You really can't trust anything. All right, so the first step in setting up a titration curve is going to be figuring out the volume at the equivalence point. So how much base did it take to titrate in order to reach the equivalence point? All right, so we know at the equivalence point, moles of acid equal moles of base. This will not occur at a pH equals 7 because you have a weak acid, you're titrating in a strong base. So your pH at the equivalence point is going to be for the conjugate base, which will be somewhere above 7. But we'll know because when we see the titration curve, you'll see the point of inflection at the equivalence point. So we're going to find this volume by plugging it into MAVA equals MBVB because the moles of the acid are equal to the moles of the base. That's the whole purpose of the equivalence point. So we know that the molarity of the acid is 0.1, and this was given to us in the problem, and the volume was 60 mils. The molarity of the base will be 0.2, and the volume of the base at the equivalence point is what we're solving for. So the volume of the base will be 30 milliliters. And you can leave that equation in molarity, in milliliters. All right, so we know that all of our points, and it's really important to find this volume before you start to calculate a pH because this is going to determine the rest of the points that we're going to need to find. So step 2 is to determine the volumes to calculate the pH for. So you're always going to determine the pH at 0 mils of KOH. And this is where you purely have just your HA. That's all that there is. So you're just going to have your dissociation with the HA. You're then going to come down and do the volume at the 30 moles of KOH. That's where it's all going to be converted to A minus. We know that that's a conjugate base, and a conjugate base will set up that's a weak acid. Both of these will set up dissociations. So we'll have to use Ka and Kb values to find these. In the middle, you're going to pick 3 buffer locations. One of the buffer locations must be halfway to the equivalence point. So halfway to this equivalence point is going to be 15 milliliters. So I'm just taking the 30 and dividing it by 2. And this is of the KOH. And this is an important part because halfway to the equivalence point is where the pH equals the pKa. And that's almost always a value that they ask you to find on a titration curve. So if you were interpreting a pH curve, this would be a spot that you would want to find because it would give you the pKa and you can solve for the Ka of that. 2 other points that you're going to want to look at are going to be 2 areas in the buffer region, and you can pick those. So I'm going to stick with whole numbers just to make life easy. So I'll have volume is 10 milliliters of the KOH, and volume is 20 milliliters, and all 3 of these are going to be calculated the same way. They're all in the buffer region. Okay, so now our third step is to actually calculate the pH at selected volumes. So we'll walk through each one by one. So the first one is where the volume equals 0 milliliters of the KOH. So you have no titration yet. So this would be the same way you could calculate the pH of 0.1 molar propanoic acid. Okay, there's no difference in calculating this because really no titration has happened yet. So we have to keep in mind the dissociation for propanoic acid, and I've written it in the HA form. So we have HA will dissociate into H+, that dictates the pH, and your A-. And I have the Ka value. I looked this up on the chart that you have in your notes, and it's 1.3 times 10 to the negative 5. That's a very important value to have. And we'll set up our ice chart. And I know some of you guys aren't setting up ice charts anymore because you know it's just going to be x squared over the molarity. But I shall set it up. Okay, so simple. This one you're starting out as 0.1 molar. That was given in the problem. 0, 0, minus x, plus x, plus x, x, x. We're going to approximate this because you always can. We're going to do to 0.1. So you're going to come over and you're going to set up your Ka. So your Ka is equal to H plus, A minus. And if you're confused on how I'm getting this, you need to go back and watch the weak acid pH calculation podcast because I go over it a lot slower there. So this is going to be x squared and this is going to be 0.1 because that's the molarity that we have here. And so we're going to multiply the Ka by 0.1 and take the square root. Alright, so when you plug it into the calculator you get x equals, and that's equal to the H plus concentration. Why that's important. You take the negative log of this and you get the pH equals 2.94. Okay, so we'll hold on to this value. We're going to kind of start here so we make sure we know what it is. And we'll come back and we'll graph this at the end. Alright, so the next 3 points are going to be in the buffer region. And these are going to be buffers where a reaction takes place. And the reaction is going to take place as you titrate in the strong base. So we're going to get rid of the K and we're going to make this OH minus. Okay, and this is going to be a reaction arrow only going in one direction. And if you're confused on this, there are plenty of videos that I have made on buffers. But since this is a strong base, the reaction arrow only goes one way, which means that we can use stoichiometry in these problems. Alright, so that is going to make your conjugate base and your water, and we don't really care about water. And so when we plug that into the values for these equations, we're going to need to use moles because the volume of the total solution is changing, so the molarities are going to change, so it's just easier to use moles. So if we take 60 mils, we convert it to liters, and we multiply it by 0.1, you're going to get 0.006 moles. And if we do the same thing for this, you're going to get 0.002 moles, and this is initially 0. So your OH is going to be your limiting reagent because you have less of it, and it just has to be in the buffer region. Okay, and we know that and whenever we subtract here, we're going to add to this side 0.004. Okay, and so you're left with this much HA and this A minus, and the whole goal of a buffer is to get similar amounts of the weak acid and its conjugate base, which is what we have here. And once we have that, we can plug it into the Henderson-Hasselbalch equation. So pH is going to be equal to the pKa plus the log of A minus over HA. And this can be plugged into molarity. So our pH is going to equal the pKa. So that would be the negative log of 1.3 times 10 to the negative 5. We saw it on a previous screen. That's just the value we looked up. Plus the log of 0.002, because it's always A minus, the conjugate over the HA. And we'll plug this into, oops, that's a 4, into the calculator and solve. Okay, so we end up getting that the pH is equal to 4.59. So that's another point that we are going to want to save. All right, so if we go to the next one, and for this one I already kind of set things up because it's the exact same setup. You're still going to have the 60 mils of 0.1 molar. That's what goes here. And this time, basically all that's changed is the volume of the OH minus. The moles of that is increased because you have more milliliters of it. And so we're going to subtract the limiting reagent here. That's all going to get used up. And this one's going to be 0.003, and this one's going to be 0.003. And we know this is our HA, this is our A minus. And we know that this is going to be a very, very, very important point, because where the volumes of, the moles of HA equals the moles of A minus, that means that your pH is directly equal to your pKa. So you can just take the negative log of the 1.3 times 10 to the negative 5. So the pH at this point in the buffer region is going to be 4.89. I calculated that before. 4.89. So we need to make sure that we star this so we can find this point and graph it. And again, that's very important in the buffer region. That's a very important spot. And we go to the last one in the buffer region, and again, this value has not changed because you're still starting with the same amount. You're not changing the amount of acid that you have. You're just neutralizing more of it with more of the base. Okay, so you'll subtract. Still, all the OH is used up because it's going to be your limiting reagent. So you have 0.02, 0.004, and you're going to plug this back into Henderson-Hasselbalch and get a value. So pH equals pKa plus the log of 0. So this is your A minus, whoops. This is the A minus, and this is the HA. So 0.004 over 0.0, whoops, I plugged that in, 0.02. So we get the pH is equal to 5.19. And this makes sense because in your buffer region, your pH should go up slowly and steadily. So it's not a huge jump, but it's still making an increase. The next podcast is going to pick up because we're at the maximum time. We're approaching the maximum time limit, and we'll figure out how to calculate the pH of the last spot and how to put together our graph.